How does a system powered purely by millions of tiny random guesses manage to produce highly structured, logical answers? When a large language model solves a problem, it isn't following a rigid step-by-step program. Instead, it feels the gravity of the correct solution. The internal generation process looks less like a calculator crunching numbers and more like a marble naturally rolling down a sloped terrain until it settles at the lowest point. Looking at artificial intelligence through this lens moves it out of the realm of computer tricks. It allows us to measure its behavior using the tools of physical science. We are already deploying these models to tackle critical tasks, from discovering new pharmaceuticals to writing complex software and running digital infrastructure. But we have a serious trust issue. The exact internal decision-making processes of these systems remain opaque. Traditional software relies on strict coded pathways, like a train locked onto branching tracks. Modern AI models navigate through a hazy cloud of probabilities, guessing their way forward. If these models are just predicting the next word based on probability, it is a mystery how they string together complex logic without wandering in endless circles. Until we identify the principles guiding their navigation, AI agents will remain clever engineering hacks. We need a reliable way to map their behavior. To figure out how they navigate, researchers zoomed out from predicting individual words to look at states, complete snapshots of an AI's context at any given moment. Within its parameter space, the AI learns to assign a hidden score to every possible state it could transition to next. This hidden score creates what is called a potential function. It forms a literal three-dimensional landscape, mapping the quality of different ideas. This diagram illustrates a concept from physics known as detailed balance. The AI flows from high-energy, poor states toward low-energy, optimal states. Tracking the model moving between states, transitions cancel each other out in a closed loop, acting as if in physical equilibrium. The model navigates by sliding down a topological map it built during training, a mathematical journey toward the lowest possible energy state. To test this, researchers designed a word game experiment. They tasked different models with generating a word where the numerical values of its letters add up exactly to 100. By tracking thousands of transitions between the words the models generated, the team could map out the internal landscapes of each AI. This network graph shows the AI categorizing its choices. Blue arrows mark transitions moving downhill toward better answers, while red arrows indicate moving uphill, further away from the goal. Models like Claude and Gemini showed highly convergent behavior, immediately dropping to the lowest point of the valley and staying there. But GPT-5 Nano explored widely, sloshing around the slopes, evaluating hundreds of words while maintaining perfect zero-energy loops. Across these different models, the generative process aligns with this same underlying mathematical structure. They are all navigating according to these shared principles of equilibrium. To be clear, the AI is not experiencing literal physical gravity. This is a mathematical analog of how physical systems behave. But this equivalence is highly useful. It explains why models sometimes suffer from low-temperature trapping, falling into deep, localized potholes in the landscape, and getting stuck in repetitive, incorrect loops. Because scientists can now measure this gravity, they can actively intervene. They can mathematically tilt the landscape or inject digital heat to force a trapped AI out of a rut. Controlling this temperature lets engineers dial the model's behavior. You can turn the heat up for creative brainstorming or freeze the landscape to ensure strict logical output for math tasks. Mapping this energy landscape shifts artificial intelligence from a black box we hope works into a precisely controllable instrument. In the coming years, we may see physicists studying neural networks as their own kind of thermodynamic universe. An AI's behavior is guided by an underlying implicitly learned landscape seeking equilibrium. It relies on natural flow rather than a pre-programmed set of human rules. A moment of wonder. The same statistical balances that govern the physical world appear to have taken root in our digital ones. The illusion that an AI possesses a master plan is really just the inevitable result of a complex system rolling downhill. To truly understand the future of artificial intelligence, we have to stop thinking like coders and start thinking like physicists.